So I'm going to talk about a orchard problem and some relation with the web geometry, which is coming from somehow algebraic geometry and differential geometry. But what I'm going to do is very elementary, actually. It's not so deep tools. The orchard problem has a long story, and it goes back to Jackson and Sylvester, where they independently asked a question that how we could plant actually 9 trees in a garden such that the number of rows containing exactly 3 trees to be maximum possible. So here, for example, if we translate to the mathematical language, it means that we would like to put endpoints in the plane in such a way that the number of lines passes through exactly 3 points to be maximum as possible. So look at the blue lines here. Any blue line here contains 3 points. We call this line tree-rich line. And black lines contains exactly 2 points of the given set. So to be more precise, I just give a definition. By a k-rich line, I mean a line which intersects a given set in exactly k points. And if k is 2, it's called ordinary line. We denote by tk the number of k-rich lines that a set of points can be defined. Usually, we are working with the finite sets. I have to mention this in the beginning. So let me give you some examples of sets in the plane with too many tree-rich lines. We will see what I mean by too many. So first, let me look at an irreducible smooth cubic curve. So it's called it also elliptic curve. It's known that there exists a group structure on the curve such that one can decide when 3 points are collinear or not. In other words, one can define a group on C such that 3 points P, Q, R on C are collinear if and only if the sum of them in respect to the sum of the group to be the identity element. And now if we apply the Bezout theorem, by Bezout theorem we know that any line in the plane must intersect a cubic curve in exactly 3 points by counting the number of multiplicity. So for example, a tangent, simple tangent line count twice, and if this point is an inflection point, then the tangency must be 3. Now let H be a subgroup of C of order n. Then, because we know that any line intersects this in at exactly 3 points by counting multiplicity, then we have this relation between the number of ordinary lines and the number of tree-rich lines. And if you look, any tangent line, if the point is not inflection point, must count twice at the tangency, and by Bezout theorem must intersect in one more point. Therefore, we get 3 points. 2 points, 1 point with multiplicity 2. And because H is a subgroup of order n, for any points on the subgroup which is not inflection point, any tangent line at that point must give us an ordinary line. Therefore, one can see that if we denote by W the number of inflection points in H, the number of ordinary lines counted by this formula and the number of tree-rich lines are coming from this formula. Therefore, we can see that the number of lines passes through exactly 3 points must be given by this big number. And when I'm talking about too many tree-rich line, it means the number of such a line must be of order n square. Here, another example is again coming from elliptic cubic curve. So if I consider these 3 parallel lines, then one can see that these 3 points, and if I take arithmetic progression on each of this line, then one can see that these 3 points are on a line if and only if they satisfy in this equation that a plus c 2b equals 2 times of b. And if I consider a conic and this line, then one can see that these 3 points, 2 points on the conic and 1 point on the line, are on a one line if bb equals to minus a times c. And this formula comes from this formula actually. So if you look, all three examples that I mentioned are contained in a cubic curve. Moreover, we have this result by Green and Tao, where they proved in 2013 that if you have a set of n points in the plane, then the number of three-ridge lines must be bounded by this number that we already saw this coming from the subgroups, actually coset of a subgroup of an elliptic curve. And this is the only example that can gives us the maximum possibility. Now let's generalize this result to a higher dimension. And most of my talk is about the generalization of this problem in higher dimension. So suppose that we have a set of points in RD. If a hyperplane intersect P in exactly d plus 1 points, then we call that plane a d plus 1 ridge hyperplane. And I'm going to provide first some examples with too many d plus 1 ridge hyperplanes in R3, for example. Then one can generalize this to any dimension. So first example comes from degree 4 curves in a space which are the intersection of two quadric surfaces. So by quadric surface, I mean if I want to go to homogeneous space, then projective space, then it's a homogeneous polynomial of degree 2 in 4 variables. So let S1 and S2 be two generic quadric forms. Then generically, the intersection of them must be a smooth degree 4 curves. So I denote this curve also by gamma. Then it is known that actually there exists a group structure on this curve such that 4 points P, Q, R, S on gamma are coplanar if and only if the sum of them be the identity element. Then again, if we deal with a subgroup of gamma of size n, we would be able to construct subsets with this number of 4 ridge planes. So again, I have to mention that the example comes from the intersection of two quadric surface, which is a curve of degree 4. Another example is an example as follow. Let R1 and R2 be set of points, each projectively equivalent with regular m gons, one in this plane, z equals 0, and the other in the z equals to 1. In other words, we can assume actually R1 contains in this circle sigma 1, and R2 also is contained in a circle given in by sigma 2. Therefore, if I consider union of sigma 1 and sigma 2, I can parameterize them as this formula. And one can define again a group structure on sigma 1 union of sigma 2 as this formula. The main property of this group structure is that if I pick 2 points from sigma 1 and 2 points from sigma 2, then these 4 points lie on a plane if and only if the sum of them to be the identity element of this operation. And the identity is 1, 0. Again, if you look at this example also is the intersection of two quadrics. One quadric is a union of these two planes, and the other is a cylinder containing these two circles actually. And in 2019, Conrad and Lin, they proved that actually if P be a set of n points in real projective D space, so we consider, for example, dimension 3, then the number of D plus 1 ridge hyperplanes must be bounded by this formula. In particular, they show that the maximum is attained only by subgroups of elliptic normal curve or rational eknodal curve. And these two curves are also the intersection of two quadric surfaces in dimension 3. And in higher dimension also, I will tell you that they are intersection of a certain number of quadric hypersurfaces. So therefore, I just summarize again. In the planar case, we saw that there are some examples which are contained in cubic curve with too many tree-rich lines. And in dimension 3, we saw there are examples contained in some degree 4 curves, that these degree 4 curves come from intersection of two quadric surfaces. In other words, in each of these examples, we saw that there is a group structure that describe coplanarity in the space case and collinearity in the planar case of 3 and 4 points. So it's also a conjecture by Ben-Green and Elekes Szabó in 2012 or 13 that if we have a set of points in the plane with no k points on a line, and assume that this set spans as many delta n square lines meeting P in at least 3 points or exactly 3 points, it doesn't change the result at all, then there exists a cubic curve that this cubic curve must contain c times n points of P, which this c depends only to delta and k, which we fixed it in the beginning. So there is some evidence that confirms this conjecture. I have to say that this conjecture, even if we replace this delta n square by 10 points, this Cn by 10 points, still is a very difficult conjecture to prove. So the theorem of Elekes-Szabó says that if we have a curve, algebraic curve in the plane that contains a set of n points with too many tree-rich lines, then the curve must be actually a cubic curve. And in order to prove of this theorem, they use two tools. One tool is called Graf-Zauer, which proved in 1924 and rediscovered by Elekes-Szabó in 2013, which says that whenever we have a curve that the collinearity between 3 points on it can be described by a group, then the curve must be an algebraic curve of degree 3. So first, it's forced that the curve must be algebraic, and second, the degree must be exactly 3. The next tool that they use is called Elekes-Szabó, which is a fundamental result in discrete geometry. And this theorem says that whenever we have an irreducible algebraic surface of degree d in 3 variables in complex numbers, then either the intersection of 0 set of this polynomial with Cartesian product is small, or if it is too many, then there must actually locally a group structure on a point set of the ZF. So here we could write down the points of ZF by this formula, where phi i's are analytic functions from some intervals to complex numbers when or reals when we reduce to real numbers. So there is a generalization of this theorem in higher dimensions, and I'm not going to talk about that. And mostly I'm talking actually to generalize this result to higher dimension, and then I use that result with generalization of this result to came up with my result. But before that, I give you some definitions. So first of all, when I'm again recall that by quadric hypersurface in projective space, I mean the zero solution of a homogeneous polynomial of degree 2 in d+1 variables. And an algebraic curve C of degree d+1 in projective space PD is called first species if it is the intersection of exactly d choose 2 minus 1 quadric hypersurfaces. And there is an analog of the Green and Elekes-Szabó conjecture, where that if I have a set of points in d dimension, it's not too many on a line, and I assume this set spans too many hyperplanes, which are d plus 1 reach, then there must exist a fresh species curve containing at least c times n points of C, where C again is a constant dependent to K and delta, which we fixed in the beginning. For example, in dimension 3, so D is 3, so we would expect that the first species is the intersection of two quadric. So it's a degree 4 curve, which comes from the intersection of two quadric. Because there are some degree 4 curves that only one quadric could be contain this curve. So this means that every curve is not really a first species. So this is the main result of mine with Conrad, that let delta be a fixed number and let C be an algebraic curve of degree m in Rd. And suppose that this curve accommodates a set of points with too many d plus 1 reach hyperplanes. Then we will show that actually the degree must be d plus 1, and not only the degree is d, we know the degree, we know that the C must be first species, namely it is the intersection of d 2 minus 1 quadric hypersurfaces. And of course the converse of this also true, namely any curve with this property has a group structure, and then with dealing with the subgroups of that, we came up with subsets in Rd with this as many as d plus 1 reach hyperplanes. So in order to prove this, similar to planar case, first we have to discover when we are able to describe co-hyperplanarity of d plus 1 points on a curve by a group structure. So later I will rephrase this sentence more mathematically to be more understandable. And second one is a generalization of the Elekes-Szabó. So let me give one definition. By a standard system, I mean let delta I be some continuous functions from some interval around the origin to projective space, actually in Rd, and let delta 1 bar up to delta d plus 1 bar be the image of these continuous one-to-one functions. We say that these d plus 1 tuples of curves define a standard system if for every x in the domain, the values of delta I are distinct. And second, if I draw a hyperplane on any of these delta I, then it must intersect the other delta j's in at most 1 point. So it means there is no hyperplane intersecting one delta 1 in 2 points, for example. So this is some local property. So in the planar case, so it's a standard system in the plane. So around this red line, I could draw a small neighborhood such that any line intersects each piece of curves in exactly 1 point. And then we say that actually the co-hyperplanarity between delta I bar can be described by a group if there exists some functions, or if there exists a parametrization, let's say, from each of these delta I bar, such that d plus 1 distinct points, one from each component, are co-hyperplanar if and only if the sum of image of them in the group equals to the identity element. And in this setting, the first result of us is that whenever we have a standard system of continuous functions in d dimension, which is defined in an interval around the origin, and assume the co-hyperplanarity between d plus 1 graphs, delta 1 up to delta d1 plus 1, can be described by a group, then this union must be contained in a fresh species curve. So these piece of curves are not arbitrary. Then they must be first algebraic and be part of a curve, which this curve has degree d+1, and to be the intersection of exactly d choose 2 minus 1 quadric hypersurfaces. This is the first result we will need, and later I will rephrase this in a dual version, which is simpler to prove. So first I give a dual definition of the standard system, which is in literature is known as a web. So by a d+1 web in a domain U of Rd, we mean a d+1 family of leaves which are given by level sets of some smooth functions of d variables, such that through each point in this domain, exactly one hypersurface from each foliation, for example, from f1, from f2, 1, and ft+1, hypersurface passes through that point, and also the normal vectors of this hypersurface passes through a point in U must be in general position. So in my talk, everything can be proved for hypersurface, but I'm focusing only on when these level sets are hyperplanes. So for example, in dimension 3, they are planes. In the planar case, they are a line, for example. So as a one example, I can a planar one. So a planar web, tree web, can be defined as follow, that F1 are horizontal lines, F2 are family of vertical lines, and F3 are family of lines parallel with y plus x equal to 1. And namely, they are level sets of these three smooth functions. So there is a subclass of webs which are important, and a generic web actually doesn't have this property, and we call this we call them regular web. So by regular web, d+1 web, we mean that suppose we have a web and a d+1 web, and assume there exists a group G and some maps from this family of hyperplanes to some group G, such that this group could be described intersection of these hyperplanes, namely d+1 web, one web from each foliation, are concurrent if and only if the image of them in the group is 0. It's the identity element in the group. This is not difficult to show that whenever we have a regular web, then the foliation, that the level sets has a simple form. Actually, one can assume the first d foliations are a coordinate system. Then we could be able to show that the last foliation gives by this formula. And this is very helpful to simplify the argument. And there exists actually a nice explanation for a regular web in terms of geometry. Somehow, I just here mentioned the dimension 3. So we have a regular 4 web of planes in some domain of the space. First of all, I draw a tetrahedron. I call it this delta, by the planes of the web. So this is the one I mean. Now I parameterize the planes in F1 by P, the planes in F2 by Q, the planes in F3 by R, and the planes in F4 by S. Then I fix one of the bases. For example, the basis in the plane from the first foliation, I call this P0. Now I use the planes from the other 3 foliations to draw a triangle in this base of delta. Then this triangle divides the base of this tetrahedron into 4 smaller triangles. So here I have one central triangle and 3 corner triangles. Now I use the planes of the web to define to construct a tetrahedron over any of these corner triangles, namely the one this within the delta. So it is a small tetrahedron over this triangle with all vertices on inside of the original tetrahedron. Second over the second triangle and on the other triangles. So we have a three smaller tetrahedron over these three corner triangles. Now we came up with new 3 points. And actually, because of regularity, one can show that there exists a plane from first foliation passes through these 3 points. So any 3 points always are coplanar, but here this plane also belongs to the first foliation. And now if you look at this picture contains an octahedron which is inscribed inside the tetrahedron. And we will see that the octahedron has a nice property regarding to the tangency to the quadric surfaces in dimension 3. So now in this setting, again, I rephrase our result about a group structure. Suppose that we have a regular D+1 web in RD, in some domain of RD. Then regularity implies that the hyperplanes of this web are common tangent to D choose 2 minus 1 quadric hypersurfaces. In other words, they are common tangents of a first species curve. So in dimension 3, for example, D is 3, so we get actually 2 quadrics, and we have a degree 4 curves, which is the intersection of the 2 quadrics. Now let me, in order to prove of this, so first I'm trying to prove this result, and then I combine this result with Elekes Szabó result in dimension D to came up with the main result that I mentioned already. So to start the proof, I first define what does it mean, the triangulation in R2. So suppose that I have a web, a tree web in the plane, which is a regular web, and I denote by delta a triangle with vertices at ABC, which this triangle constructed by lines in these 3 webs of lines. So maybe I show this picture. Now I choose, for any n bigger than or equal to 3, I choose n minus 1 lines from each family or each foliations to divide this triangle into n square smaller triangles. This is a D5, for example. So this is 4 triangles from one foliation, 4 other lines from another foliation, and 4 lines from third foliation. And this lines divides ABC into 25 smaller triangles. So these are the triangulation of in the D equals 2. Now I'm trying to generalize somehow this in dimension 3. So in dimension 3 is a bit more complicated, but still is not very complicated. Again, I start with a web, a 4 web of planes in a space, which is, I assume, also regular. I parameterize the first foliations by P, second foliation by Q, third foliation by R, and last foliation by S. I draw by this, I pick 4 planes from these foliations to draw a tetrahedron in the domain. And I call by P0, Q0, R0, S0 the faces of this tetrahedron. Now, I consider P0 as a base of this tetrahedron. And for each n, I describe dn inside of P0. So for example, this is a D5 inside of the base of that tetrahedron. Now, alternatively, I color these small triangles. And over any of these red triangles, I construct a tetrahedron within the original tetrahedron, which I started with that. Then by regularity, one can see that there exists a plane P1, let's go back again to here, that passes through all these new vertices. Now in P1, I describe dn minus 1, which contains n-1 square small triangles. Again, I alternatively color these triangles and construct a tetrahedron on each of these triangles to come up with some new points. Again, I draw a planes, and I continue this process until I came up with a figure T2 in the plane Pn-2 and triangulation a D1 in the plane Pn-1. So I take the union of these figures. I call this En. So En has some property. For example, En contains n-1 planes from each foliation, and each triangle is bounded by an octahedron and tetrahedron. The most property for me is the last one, that 4 planes in this configuration are concurrent if and only if the sum of indices is n. And this is some things I need later to prove the main result. So I go to the proof. What I want to prove. I'm just trying to prove the dimension 3. Then with some more calculation, we can generalize to a higher dimension. So suppose that I start with a regular 4 web. The goal is that to find 2 quadric surfaces such that every plane in this web is a common tangent of these 2 surfaces. To prove this, actually, first I show that for every n, En, the planes appears in En are common tangent to these 2 quadrics. Then I use continuity property to prove that all planes actually in the web must be common tangent of ZQ1 and ZQ2. So the goal is to find Q1 and Q2. So in order to prove, we need a generalization of a Chasles theorem to dimension 3. The Chasles theorem says that whenever we have 2 cubic curves, so generically they intersect in 9 points. And if there exists a cubic curve passes through 8 points of these 9 points, then it must also passes through the 9ths. So a higher dimension version of this theorem in literature call it Cayley-Octa theorem, which says that suppose I have a quadric surface which is tangent to 7 faces of an octahedron. Then it must be also tangent to the last face of octahedron. In other words, being tangent to the faces of octahedron impose only 7 conditions on the space of vector space of quadric surfaces, and not 8 actually. So the proof is by induction. I start with E3, and in E3 actually I have a P0, P1, P2. I ignore P2, I will tell you why. Q0, Q1, Q2 from second foliation, R0, R1, R2, S0, S1, S2 from last foliation. The goal is that to find 2 quadric surfaces such that any of these planes is a common tangent to these 2 quadric surfaces. Recall that in En, we will have this property that 4 planes are concurrent if and only if the sum of indices is n. So for example, if we deal with E3, then n is 3. So actually, any quadric surface, the equation of any quadric surface has 10 coefficients. And because we have one equation, so we would expect the vector space of quadric forms in 3 variables to be a non-dimensional vector space. And whenever we put one tangents property, we would expect to get one less dimension, the dimension reduced by -1. So unfortunately, in 3 dimensions, it's not easy for me to describe the figure. So I try to figure out a perspective of the picture. So I started with a tetrahedron. And now if project this tetrahedron in P0, then we came up with this labeling of the planes in the tetrahedron. So here one foliation is P0, P1, P2, but I forget P2, just I try to figure out P0, fix P0 and P1. And I show that all planes between P0 and P1 from any foliation must be common tangent. Then I just exchange the role of P with Q, for example, Q0, Q1, then to prove that actually the planes from first foliation also are common tangent. So now look at an octahedron over this triangle T1. So the octahedron over this triangle, the faces of this octahedron must be contained in these planes. One is P0, P1, and Q1, Q2, R0, R1, S0, S1. So I just write down here. So here I had a triangle. I construct an octahedron there, and the faces of this octahedron lies on these planes. By Cayley octa, we know that if a quadric surface is tangent to 7 of them, then it must be also tangent to the 8th. So therefore, this set of planes just imposes 7 conditions on the space of quadric surfaces. And therefore, if I call V to be this, the vector space, which are tangent to, that any of these planes are tangent to that quadric, then the dimension of V must be actually 2. So V is a 2-dimensional vector space. And any quadric in V has the property that any of these planes is tangent to that quadric surface. Now I consider a subset of V, a subvector actually, a subvector space of V, which is the all quadrics such that Q0 also is a common tangent to them. So now I have a set of 9 planes, already these 8 planes P0 up to S1, and I add Q0 to this. So I came up with 9 planes, and these 9 planes one can show that they impose 8 conditions on the space of quadrics. Therefore, S has dimension 1. So it means there are 2 quadrics, for example, F1 and F2 in S, such that any quadric in S can be presented as a lambda times F1 plus mu times F2 equals to 0. So in the rest of the proof, we try to show that any planes in the web are tangent, common tangent to the elements of S. So we already started with T1. Now I consider octahedron over T2. So the octahedron constructed over T2, the faces of that octahedron lie on these planes, P0, P1, Q0, Q1, S1, S2, and R0, R1. And P0, P1, Q0, Q1, R0, R1, and S1 already appeared in T1. Let me just, here. So here. So these are the planes containing the faces of octahedron over this triangle T2. So then S2 here is a new plane. And we know that P0 up to S1 are common tangent to quadrics in S. But by Cayley-octa theorem, we know that actually S2 also must be a common tangent to any quadric which is a tangent to these first 7 elements. So therefore, we don't get any new linearly condition on the space of quadrics. Next step, we could consider an octahedron over T3. So octahedron over T3 also the faces of this octahedron contained in these planes P0 up to R1 and R2. Again, the first 7 faces already are tangent to any element in S. Therefore, if I pick one element from S, the vector space S, that quadric is tangent to 7 faces of this octahedron. Therefore, by Cayley-Octa theorem, it must be tangent to R2 as well. So now I prove that actually every planes in E3 is a common tangent to elements in quadric surface in S. Now we could go through E4. So in E4 also, here if I draw a perspective of the E4 in the plane P0, then one can see that in E4 we came up with these planes R0, R1, R2, R3, and Q0, Q1, Q2, Q3, and so on. Sorry. Again here, one can see that actually if I consider AFG, then this triangle is a copy of E3, right? Therefore, we have to show that the elements in the Q0, S3, R3, and Q0, S3, R3 are the also common tangent to elements in S. Again, if I consider octahedrons over T4, T5, and T6 as a E3, we can prove that really they are also common tangent. So I just skipped the one. So then by applying induction, we could show that every element in En also is a common tangent to every quadric in S. Furthermore, if I consider E to 2I, then we can see that actually E to 2I is a subset of E to 2I plus 1. And this is gives me a dense subset of planes which are common tangent to every element in S. Then I can use the continuity of the plane of tangency to show that all elements actually in the web are common tangent to elements in S. So far now we know that whenever we have a group structure which describe co-hyperplanarity of 4 points, then they must be the intersection of the two quadrics. But if this is a curve of the degree 4, which is the intersection of the two quadrics. Now let me rephrase again, recall that the main result that we are looking for. The result that I mentioned was this. Suppose that delta is bigger than fixed delta, and let C be a curve of degree m in Rd. And suppose that there exists a subset of n points in C that determines this number of d plus 1 rich hyperplanes. Then M must be d plus 1, and also C is the first species curve. So by Elekes Szabó, we know that, so in dimension 3, so we have a 4-dimensional polynomial. Now if I have a 4-variable polynomial of degree d, then the intersection of this hypersurface with this Cartesian net is either small, or it has some locally has some group structure. So namely we could define this in this form. Now let's go back to our problem. So in our problem we start with a curve which is algebraic of constant degree d. And we know that 4 points xi, yi, zi in C lie on a plane if and only if the determinant of this matrix to be 0. Now we could arrange some projection to came up with the polynomials of 4 variables. And because we have too many tree-rich lines, if I consider the first coordinate of each of these points appearing in these planes, and we call this set by A, then one can see that the 0 set of F intersect this Cartesian in too many points. Therefore, by this result, we conclude that there exists a group structure on the curve. And because we have a group structure, it means we have a regular web. And since we have a regular web, we conclude that the curve must be d plus 1 and also first species. And